In this proposal, I present my idea of how I would make a space elevator as simple as it is possible to imagine. I will begin by describing how I would start the construction from the geostationary point, kilometer 36,000, until I reached the kilometer where I would locate the apex anchor, and where I would place the anchor on the Earth's surface. I dare to say that Panama would be a good candidate for the location of this space elevator. This country offers many positive qualities that make this project viable. We are close to the geographical equator, we do not have earthquakes or hurricanes, we are the air hub of Latin America, and it is not a simple coincidence that we have here the Panama Canal. I am convinced that using a system very similar to the stay insulator in a space elevator would be a viable solution to the tethers problem. Since the tether would not have to measure 100,000 continuous kilometers, with this system it would be 37,000 kilometers plus 63,000 kilometers, without the width of the tether varying. Let us imagine that initially, with the help of astronauts and sending the pieces from the Earth's surface past the geosynchronous point, before 37,000 kilometers. A structure of strong and light material, carbon fiber or similar, was built very similar to a stay insulator, which will serve as an anchor for two robot assemblers to build the tether. With this system, the robots will be armed and strongly attached to this stay insulator type structure, so that one is pointing towards kilometer 100,000, and its twin will be pointing towards the surface of the Earth, in this case Panama. In addition to this anchorage, a tie will be included that goes from the stay insulator structure to each assembly robot to give greater rigidity and support to the entire structure. From the Earth's surface, 4 rolls will be sent that form a cylinder containing 500 meters of tether. These rolls will be attached with the help of astronauts to the assembly robots, and once attached, the assembly robot will weld the final 30 meters of the previous tether with the first 30 initial meters of the new shipment. Important note: the proportion of sending these 500 meters of tether to the assembly robot will be 2 to 1. For every 2 that go towards kilometer 100,000, 1 will go to Earth. From the surface of the Earth, reusable rockets are launched that carry the Roten C9 rocket on top that has some modifications, such as not carrying a crew, among others. The rocket will take the Roten C9 to low orbit. From there the Roten C9 will continue its journey until it docks with the end of the tether coming out of the assembly machine. In this proposal, we present a rocket model that uses the same system as the Roten C9 but in the booster rocket, and with the help of its main engine plus the propeller system. It will provide a very smooth and precise landing. The beginning of each tether has a multidirectional robot, whose function is to join or attach to the Roten C9. Once joined, the function of the Roten C9 is to pull the tethers as they come out of the assembly robot to avoid build-up, tangle or cut. And at the moment in which the robot begins its process of extracting the tether, the assembler robot will send a signal to the Roten C9 so that they begin to pull the tether towards their destinations. This is with the objective that it does not accumulate the tether and prevent it from becoming entangled or broken. Important note: When the Roten C9 is about to run out of fuel, a new one is sent from the Earth's surface to replace it, in the case of those who travel to the apex anchor. The replacement consists of attaching the new rocket above the one that has already run out of fuel, with the help of astronauts or autonomously. This process of sending cylinders containing 500 meters of tether, which are sent from the surface to the assembly robot, will be repeated continuously until forming the 100,000 kilometers from the apex anchor to the surface of the Earth. While all this process is taking place in space, simultaneously on the surface of the Earth, an F-type nuclear silo-style anchorage will be built. This in order to give greater security to the personnel and structures that make up this structure. Important note: the astronauts are to scale to give an idea of the dimensions. Option B of this proposal would be the construction of a marine platform in the territorial Sea of Panama, which we will use for this proposal. In this proposal there are two types of climber, cargo climber, and help climber. As its name indicates, the cargo climber carries two containers with a capacity of 40 cubic meters. And the help climber carries a nuclear cell, which will power both climbers with electricity. And as its name implies, it helps the load climber to go up and down when gravity is more intense. Each climber has 8 electric motors, 4 above and 4 below, that press the tether from its opposite angle. This creates a deformation in the tether that the climber takes advantage of to create traction in the tether and be able to go up and down reliably. As each climber is composed of a pair, cargo climber, and the help climber. This gives us 16 electric motors that pressure the tether to obtain more grip or traction, making it more reliable for this task. Meanwhile in space, after the maritime platform, or silo base, on the surface are already finished. In the last few kilometers that are needed to connect heaven and earth, in this example we will say 1,000 kilometers. They will attach to the tether the necessary number of autonomous multidirectional rockets that pull towards the Earth anchor. The tether and correct the course so that they leave the tether as close as possible to the Earth anchor. When these multidirectional rockets, plus the tether, reach the Earth's surface, they will be anchored, either using option A, or option B. Important note: this action will be carried out before the arrival of the tether at kilometer 100,000. Once the tether coming from the geosynchronous orbit, GEO, is connected and secured to the offshore platform, or silo platform, the other end of the tether will be located, let's say, at kilometer 80,000, and the assembler robot will continue to receive raw material to continue creating the tether until reaching kilometer 100,000. Important note: the assembler robot will receive material on the side, already connected to the Earth, to move away from kilometer 36,000 to kilometer 37,000. The reason is because the stay insulator type structure in the assembler machine will form perennial part of the structure. In other words, the climber will not pass the 37,000 kilometer. When the other end of the tether reaches kilometer 100,000, it will be composed of around 10 or more Rotan C9, which will also be an integral part of the whole system, since these Rotan C9 will serve as apex anchor. Important note: if each Rotan C9 weighs about 25 tons, in this representation we would have a weight of 250 tons. If more were needed, we would simply send more of these rockets. And this is how it works. From the structure on Earth, either option A or option B, the climbers, loaded with merchandise, will leave towards kilometer 36,000, geo. It will take the climber about 7 or 8 days to reach kilometer 36,000, geo. Once the climber reaches kilometer 36,000, geo, an autonomous robot will unload the merchandise from the climber. This process is in both directions, from the surface of the Earth to space, or from space to Earth. 1,000 kilometers above the geopoint, the assembly machine will be located. Since the assembly machine is a permanent part of the structure in this location, it will not interfere with the space elevator mission. And finally, at kilometer 100,000, we will find a number of Rotan C9 that will serve as apex anchor. And in this representation we will say that with 10 of these Rotan C9 it is enough to complete the apex anchor.